My wife bought her 2006 Corolla in, I don't know, 2006 or 2005. She had it longer than she had me, our relationship, and she loved that car. It got old and we got a new one. But while we still had it, we were sharing it. And this was back when we lived in Arlington, right on Columbia Pike by the Air Force Memorial. So to get to there from here on the way home, sometimes we would go Walter Reed, and then we'd go up this hill right there on 4 Mile Drive. It's a hill, like it's kind of steep. I mean, it's not like San Francisco, but it's a hill. Something like a 17-degree incline on average. Just judging from the topographical map and a little bit of Google Maps work. So I did look this up. I'm not about to lie to you with this up there. That's real stuff. I could, but that doesn't seem right. Getting up that hill at 30 miles an hour in this 2006 Corolla, like a couple of years ago, was hard on the car. You know, you driving on the flat road, Walter Reed going up. You know, coming up to the hill was fine, but then as soon as you get on the hill, it was like trying really hard to see the RPMs max out. You know, but it could do it. So my question to you: how much steeper could it have been before the Corolla just would not have been able to keep 30 miles an hour?
So would it slow down?
It would
Wait,
slow
ask
down.
that again?
Would it slow down?
So 17 degrees, Corolla can do it. What if it's 18 or 21? Is there a steepness that's too steep for the car? Like it just, the engine can't do it.
Well, when does the engine?
But the engine.
Not that it blows up, it's just, but it can't keep speed.
But how do you supposed to know what that is?
We're gonna find out. I'm not gonna ask you to answer it right now. We gotta do a bunch of work first. 5 pages later, we're gonna answer that question.
Fine. Oh, no.
So part of the problem is that we don't have a good way to talk about how hard the engine is trying. Right? Like that's a perfectly nice thing to say, and you have some experience with it, right? You can hear the car like being loud, you can see the RPM ping up, and I guess that's like a way to check how hard it's trying. But we don't really have a physics thing to do this. So let's define one.
I'm sorry, is this still chapter 4?
No,
5?
7.
7? Okay, because I was like, I don't remember.
Remember, I said we were gonna skip 6?
Oh.
I didn't know.
So, wait, can you send me question?
Which question?
One to that.
Let's define a thing that talks about how hard we are trying to do a thing, how much effort we're spending.
Calorie.
Chapter.
Oh, chapter
I don't
6,
think
I'm
that.
sorry. Because I know with calorie, you put something in like a food
No,
or
chapter
maybe
4.
blow it up. You see how much energy it took for the whole thing to go away.
That's true.
And
But
that's
I
how you
was
get
that part of
calorie.
the exam.
I like that thought.
Do we need joules?
I think we're in there.
Okay.
This is in fact the energy demo. So
So we're gonna, I forgot what joules is, 4.8 per calorie, 4.8
that sounds
calories
right.
or some shit.
So the inspiration I'd like to draw from is running on the treadmill.
Already.
No. Run on a treadmill. If I set the treadmill to a particular speed, it requires some amount of effort. If I do that for longer, like if I cover a greater distance, I run, you know, a 5K instead of a 3K, I'm more tired afterwards, right? Going farther at the same speed took more effort.
Yeah, there's more stuff to do.
You did more, right? So let's just make some shit up.
All right.
The greater the distance, the more tired I get. Running at a particular speed requires some amount of, I gotta like push on my muscles and push, shit, force.
Yeah.
I gotta do force things for a distance, right? All right, cool. Particular effort, greater the distance, so effort. Let's just make something up. 3-line equals is defined to be. Why? Because we fucking said so.
It means decline.
3-line equals. This is equal because it is defined to be so. It's not equal for any other reason than we decided we were going to make that.
So if it's like, we make it up, how valid is it? Or is it as long as everything we say follows what we said prior?
Pretty much. So when we say force, that means a thing, right? It means a whole bunch of like Newton's laws kind of things, right? So we just need to stay consistent with it. We can define anything we like, as long as we chase down all the consequences of it. The name in the physics textbooks for this quantity is work. So this definition work, capital W, force, distance. We're just going to make that up. We're just going to say that this is a thing. Sorry?
Is that delta R?
It is, yeah. Because I don't know what direction we're going. So I just want to be general. Okay. How does this thing work? If we're going to make this definition, how does this thing work? I push a large box 4 meters across the room by applying a force of 235 meters. According to this definition, how much work did I do? Well, we just multiply. That's what we said we were going to do. Force times the distance. The force is 235 newtons. The distance is 4 meters. J. What the fuck is J? Joules. The units for this, newtons, meters. Or kilogram meters squared per second squared. Because a newton would be a kilogram meter per square seconds. And we just multiply it by another meters. Kilogram meter squared per second squared is a lot. So let's define another unit. Joules. The reason we named the unit of work after James Prescott Joule will become apparent in like 7 weeks.
Wow.
7 weeks. Because he did some research while the company he worked for was making beer that unified mechanics and thermodynamics. He was able to put them together in a really useful way. Because of beer. How much work did friction do on the box? Wait, who said anything about friction?
You did,
Why did I say something about friction?
because it's something, pushing it across the floor.
At
Push.
constant velocity. What a wonderful phrase. What does that mean?
Zero. is acceleration.
Acceleration 0. What does that mean about the sum of the forces? There has to be something to oppose my 235. Otherwise, there would be acceleration. The fact that there isn't means something is pushing against me.
Mhm.
Apparently, friction. So how strong is friction in this case?
235,
235. So how much work does friction do?
negative 235, wait, regular 235? No, negative 540. No. wait.
235, 4 meters, 940.
Oh, so you're just declaring. Oh. So you're just declaring that the force is friction and you get the same answer?
Here, yeah.
Okay.
There's a bunch of like conceptual reasoning that went into declaring that the force of friction is 235. Has to do with constant velocity and Newton's second law. But I trust you. I think y'all are ready for that rhetorical shorthand.
Wait, what?
This bit, the fact that it's equal to 0, and the fact that that means friction and applied have to be equal.
Yeah.
I think we can just sort of
Oh, okay, yeah.
paper over that because we know it.
Yeah.
Right.
So, and then would the network be like 1880?
So we just add them, right?
Is that what you do?
So the sum of the work done,
Yeah. And the total work, how much all together was done. So we add them, I guess.
1880 volts. What does that say?
Me. How much work did I do? Me. And the work done by friction.
Oh. Oh,
I just want to write that net work means that I add them all up. How does that feel to y'all? Does that feel okay? Okay. Feels a little bit weird to me.
What feels weird with that work?
Yeah.
Why?
Because my force and friction's force point in opposite directions. Does that matter?
I don't think so.
Okay.
Because if it's network, they just want all of it, right? Not like. It's, you know what I mean? It's like they're just asking for everything, not just how much. Not like,
Okay.
not
So,
like
like-
didn't equal 0, just what things added to make 0 makes sense.
Yeah. So let me ask, if only one force was acting, right? If I was pushing on a thing on a hockey rink, and I used 235 newtons of force for 4 meters, 940 joules of work, we're done. Okay? But after doing that, I would have accelerated that box. And after my 4 meters, it would have some speed and it would just keep going on the hockey rink. Right? So now you're telling me that double the amount of work is done. But when I'm done pushing, what happens?
It stops.
Okay. So twice as much work, but we just stop
Because.
because something.
So force.
The force stopped, because the friction wasn't great as the thing, so it stopped.
Right.
Like say friction was less than, it has left over.
Okay.
So wait, is it supposed to be zero then? Because when something does zero work, it's like dead, like stop, doing that.
So this is the question. If it isn't 1880, I think it ought to be zero.
But if it had left over, it could keep going.
Yeah. So I'm saying, what if I applied twice as much force for 4 meters?
Then
Right,
it would be able to slow.
on a hockey rink. Then I would have done twice the acceleration for however long it took to go 4 meters. And it would have more, it would be moving more when it was done. It would have a greater velocity when I was done. So a greater work feels to me like greater motion at the end. Like if more work is done, it should either go farther, like me on the treadmill, or it should be going faster when I'm done, like pushing the box on the hockey rink. So here we're saying double the work, but it just stops. Like all of this work is done on the box, but nothing happens. It just hangs out when we're done. So how do we fix this?
Is it like, do we use absolute value or something?
Come on. Force is a vector quantity, isn't it?
Yeah.
We use force in our definition of work just now.
Mhm.
So force, if we're going to chase down the consequences of the definition that we made up, force should be a vector, and we have vector stuff there. Now, okay, so hold on. If the right-hand side has vector shit going on, then the left-hand side also needs vector shit going on. But here's the thing. On the treadmill, I don't have a direction. I'm still staying like. And I think you would tell me that pushing a box this way requires exactly as much effort as turning around and pushing it back this way, which it wouldn't if we used a vector thing for work.
You said it would.
Because I get just as tired if I push it that way as if I turn around and push it this way.
Mhm.
So I actively want to avoid work having a direction, because I shouldn't care. Effort is effort,
But we use force.
but we use force.
But can we
Is
just
there a way to use not
declare
force?
that the work was done in a certain direction?
Like I don't want to say anything about direction.
Oh,
Work is work. How much work did it take? This much. I don't care what direction you went. You know what I mean? Like if I push the thing east or if I push it north, I still had to, it required the same amount of effort.
There's something bad.
Displacement
That's the one that you can.
is also a vector.
So since it's
oh,
vector,
because
it
it's just
doesn't
moving in a
cancel out.
certain direction.
We're moving, we're creating displacement by applying force. Both of those things are directional, but I have no idea how to multiply two vectors.
So we don't do anything.
So here's the thing. The textbook does not trust you with this information.
Well, that's rude.
I know, but I do.
Thanks, mister.
I know. So here's the story. We know how to multiply assigned numbers, right? Think about a number line. What's the product of -3 and 4? -12, not the sum, the product. What's the product of 3 and 4? +12. What's the product of -3 and -4? So anytime the two numbers are in the same direction on the number line, product is positive. Anytime the two numbers are in opposite directions, the product is negative.
That makes so much sense.
We already know how to multiply directed quantities. Negative numbers are to the left on the number line. Positive numbers are to the right. We already know how to do this. If they are parallel, positive. If they are anti-parallel, opposite directed, negative.
And since they both don't care, we could,
Right.
in theory, make them.
Right, because both to the left and both to the right, the answer is positive either way. All right,
You said it's parallel.
and if anti-parallel, negative.
And you're talking about the product of two vectors or just in general?
For now, just integers.
Okay.
So we know how to multiply directed quantities if they're on the same number line, by which I mean the same axis. So here I'm thinking, if I've got a vector that's 3 to the left and a different vector that's 4 to the right, I can multiply them and get -12. That should work. Because it's worked all along. Just draw little arrows on the number line. It's basically what we've been doing since the beginning.
Wait, so if they're like different directions, which way does the arrow of the answer point?
It doesn't. It's just 12.
So it doesn't
So
need.
you don't have to say a direction.
We don't have to say direction. When we say that the product is -12, we say that the product is 12 big and that the vectors were opposite.
Oh, so.
Doesn't matter which is which. And there's no direction to the result. It's just, that's the answer.
So it's never gonna be negative, because negative just means that they were in that direction.
Right.
Oh.
So we multiply 3, I don't know, 3 newtons west
Mhm,
and 4 newtons east,
mhm.
and we say -12.
Which is 12.
Right. We just say -12, and then we know what we mean.
Oh, so you don't have to say, if you put the negative, you don't have to say the arrows
Exactly.
are apart.
Exactly.
You put positive, you say they're.
Yeah.
Oh,
Okay. So if the vectors we've got are on the same axis, then I have a theory for how we can multiply them. But what if they're not? Suppose I push on this part down at an angle. Still moves. And it'll still be a force that propels the thing a particular distance. Friction is still irrelevant because it's still swaying. But the orientation is different. It's not just pushing sideways, it's pushing down at an angle. I don't know how to multiply those. Well, I know how to multiply the parts of them that are coaxial.
that was.
Here's just along the same axis. So here's what I'm thinking. Suppose we have a vector A and a different vector B. They're mostly parallel. I need a way to talk about how parallel they are. How much of B is along the same axis as A?
You just get the angle or no? Oh, okay. Made the concept of an angle very confusing for a second.
So we've got,
We got multiple times too.
I know, right? Part of B that's parallel to A and part of B that's perpendicular. Yeah. And we can do this as long as we know what the angle is between A and B. A and B parallel are coaxial. I can multiply them just like I multiply shit on a number line.
What's the little green here?
It's B. It's not theta.
What's that?
It's a different symbol for angle. I want to use a different symbol because the angle we're talking about here is not the angle at which A or B necessarily is oriented. Suppose, for example, it'll look like that. A has its own direction. That angle. B has its own direction. That angle. But the angle we're talking about is neither of those two. I would talk about these theta sub A, theta sub B, but I don't want either of those for this thing we're doing. I want the difference. I need this one. B. Or phi, but I think officially phi. If we speak the Greek. There are lots of Greek letters that we're not going to use.
Oh, is the difference in angles?
It's the relative angle between the one and the other. I don't like the
Oh.
fact that one of them is at 60 degrees. I don't care. I need to know how far apart they are.
So it's
Relative.
one that's 60 and one's at 30.
Then we would subtract.
30.
Yeah. Or if one's at 60 and the other's at 20,
You say negative 40.
then the difference is 40.
Relative distance between.
Relative angle.
Just relative angle, okay.
Not their actual orientation, but the angle between them. If we do this, then I'm going to say you tell me what you want to do is multiply vector A and vector B. I know a way to do that. I can at least give you an answer if you let me do it this way. Multiply A and B parallel
Oh,
because they are on the same number line together. B parallel, we're looking at a triangle. And it's a right triangle. And that it smells like trigonometry to me.
So is it 90
This angle here?
degrees?
Yeah. So which trig function do we need?
For the opposite of
Is
5?
it opposite or adjacent? We're looking for B parallel.
Wait, from 5 to be parallel? That's adjacent.
So we need cosine. Just out of curiosity. In the first quadrant, cosine is positive all the time?
Yes.
What about the second quadrant?
X is negative, Y is positive.
All even six factors. So in the first quadrant, it's all positive. And the second, sign is positive. And the other one is tangent is positive. So it's not positive. And then calculus is cosine is positive.
So what if we had that instead?
What does that do?
I can't really see it.
Oh, yeah.
A and B.
It would be negative.
So that's the angle between them. That's an obtuse angle, isn't it?
Yeah.
And the cosine of an obtuse angle is negative. And what we end up saying is that the product, these vectors are more anti-parallel than they are parallel. And we do end up with a negative number. Cosine is just ready-made to do this job. The symbol that I'd like to use for the new operation that we have just defined, it's multiplication, so I'm going to use the multiplication dot, like we used to use back in grade school. And I'm going to call this thing we just made the dot product.
So A vector times B vector equals A times B parallel?
Yes.
Okay.
We're going to define it that way. And when we define it, we need the magnitude of A, the magnitude of B, and the angle between them.
Is the dot product the dot itself or the equation?
It's the whole thing, right? It's like, you know how we write x with an exponent 2? That means multiply x by itself, right? We just understand that that's what that means.
Mhm.
We do the same thing. Anytime we have two vectors, we put a dot in the middle of them, we're doing this.
Oh, okay.
So we've got a new mathematical operation. Like how, when you put a division symbol, when you're talking about fractions, what you actually mean is multiply by the upside down. Same sort of deal. We're defining a thing to do whenever we see thing dot something else. We always do magnitude of thing, magnitude of something else. What's my name? We also sometimes call it the scalar product. Not because we're multiplying scalar things, but because we multiplied two vectors and ended up with a scalar. The result has no direction. It's just a number.
And is that because you don't put direction before?
Yeah.
So like for a question that had two, I don't know if this happens, but say you were using two vectors that equal something, like would it be like northwest?
Sure.
Oh,
But then we have to dot with the displacement.
oh, okay.
So we're going to end up with a numeric result, not a directed result, just a quantity. All right. So let's use this new equipment and update our definitions. With the dot. And we could write what we know that that's going to be equal to. where phi is the angle between the force and the displacement. Sometimes I do this. And I actually write subscript between, just to remind myself that I'm talking about the angle between two things, the two things in the product. The textbook. I hate textbooks to do this. And they all do it, one way or another, they all do it. The textbook just shows you that and doesn't tell you why. And I think that's crap. Where the hell did the cosine come from? What is it doing there? We're talking about things that aren't parallel, and we're trying to find the parallel components so we can multiply. That's what the cosine is there for. I don't get it. Why do we feel like y'all can't handle that? All right, well, anyway. So now that we have this new equipment, how does it work? Tying a rope to the box weighs 590 newtons. I'm able to move it with constant velocity by pulling on the rope at an angle of 15 degrees above the horizontal. This, I'm having flashbacks to this problem. We tied a rope and pulled up at an angle. That sounds exactly like this. So we're gonna have, oh gosh. This question has layers, like an onion. Exactly like an onion. Or like an ogre. Ogres are like onions. That's my terrible Scottish accent. What are we doing here? So I'm not going to ask any questions. How much work? Fine, I'm gonna write the thing for work. All right, so I need to know how much work do I do by my applied force? So I'm gonna write applied. So I know that that's going to be equal to however much force I apply, however far the box moves, and the cosine of the angle between those two things. That's because that's how we define the dot product.
So we don't need the dot after that first thing?
We do not. Frankly, we don't ever really need the dot product.
We just like to make stuff up.
And I guess that's why the textbook doesn't present it. I just find it so bogus that it's like, oh, we're going to define it as force R and some cosine for some reason. I like, where did the cosine come from? You're so close. Just tell me the whole story, man. We spent a whole chapter talking about vectors. And now you're just gonna like, never mind, don't pay any attention to that.
Why does it say the box weighs 590 newtons?
Yeah, because this problem has layers. And I don't want to do the whole thing.
Would that be how much force that the box puts onto the ground?
What, this?
Weighs it? I don't know, what if the box weight is moving?
Well, every weight is newtons because it's mass times g.
Don't tell me how much harder to be.
So what's pounds?
A different unit.
So wait, we could go by unit?
Yeah.
Just call it.
Oh, wow.
used to pounds, and we are like body weight conscious. Using newtons makes things worse.
Oh, you can bigger.
It'd be a bigger number. Yeah, if I'm 220 pounds, I'm 100 kilograms, which means I'm close to 1,000 newtons.
Nice.
But newtons are smaller.
They are, so having more of them is the problem.
So what, do people make pounds and kilograms to make it bigger? Like to make it easier to work with?
It's just because, right, it's just because the US doesn't metric.
But like even from like units to kilograms, is it to make it easier to work with?
You could do that, sure. Just gotta divide by 10, basically. It's 9.8, it's close to 10. Figuring out how much force, so wait a minute. Where did I get this? Where did I get 15? The displacement is along the floor and the force is directed up at an angle. And we're told 15, and it just so happens that the angle the dot product cares about is 15. How much force do I need to apply to do this? What is the magnitude of my applied force? I was not told. If I applied 235 newtons of force and friction also applied 235 newtons of force, that means I can figure out the coefficient of friction if I know how much the box weighs, which I was just now told. Now that I know, it's worksheet 4.4 all over again. Contained within a larger question about work.
Wait, how are you? I'm sorry, how are we gonna do that?
Sorry?
Sorry, what did you just say? About getting the weight somehow?
Well, the weight is told to us.
Right.
I'm able to move it with constant velocity by pulling on the rope at an angle of 15 above the horizontal. The last time I pulled up on a rope, I changed the applied force that I needed to use.
Yeah.
So now that I'm pulling up 15 degrees, I don't know what my applied force is anymore. It isn't 235. Because I'm still moving at a constant velocity. So I'm gonna have to go through everything we did on worksheet 4.4. Figure out how strong is friction. And then what force do I need to apply to move the thing at constant speed? So we're gonna have to do this all in order to answer this. We need to know the applied force. I don't want to do that right now.
Is there a secret way?
No. Nope. There is no secret. There is no shortcut. This is just what we're gonna have to do. Which sucks a bit. And makes you a little bit mad at whoever wrote the worksheet.
I wonder who did that.
Wait.
Worksheet. This thing. We got to do this whole strategy again. But assuming we did, using the dot product was easy. Assuming we went through all of this rigmarole, we can take that number, put it here, and we're done.
Okay, which number?
This applied force that we need to keep it moving at constant velocity.
Oh.
Whatever it turns out to be.
Oh, okay. That's why I said it's a new reality over here.
Sure, but we don't know mu yet.
Oh.
So we would
But
do
we
all
have
that
the new
fine,
piece.
that's okay, and then plug it back.
On the way to the box.
Oh,
Exactly, so we know the weight of the box, we know how strong friction was, so we can find the coefficient. And then we can plug it into that formula and change it from 20 to 15. And then, yeah. Good stuff, good stuff. It's almost like there was a plan for worksheet 4.4 all along. Onions,
all a scam.
onions on onions.
God. This is why we're crying.
Don't cry. It's good. It means this work that we did on 4.4, it wasn't just for nothing, right? We just, oh, I got the answer and I'm done. No, we were gonna need it.
For the onion. It's our right for the.
The answer just points to the next question.
It's like an escape room.
So, in the last 3 minutes,
No matter.
I'd like to present the consequences of the choices we made.
But like, was this the only choice in the list of cons?
No, we just made up work. Like we just defined it, and then we were like, oh, fuck, it's a vector. I need a way to multiply vectors. Okay, I'm gonna make that up too.
So, yeah, I feel like we're just making stuff up this whole time.
Pretty much.
And that's why it doesn't make sense to me.
So wait, like,
See where you're
It's like we have to crying out onions.
Yes.
Like why?
Maybe like force multiplied by the time over which we apply.
What did you say? It's short.
Yeah.
So is force the only way to get work?
That's a complicated question. No, but we need more areas of physics in order to solve that. Suppose we asked for all the work. Add up all the work done by all the forces. Wait, did you say all the forces? Like the net force? Yeah, and then you gotta dot that by the displacement, yeah? Net work is what you get if you find first the net force and then dot that with the displacement. So actually, wait a minute. We gotta go back. On the first page, friction, according to our new dot product thing, friction is always opposite the way we go. Friction did negative work. Because the angle between friction and the way we went is 180. And the cosine of 180 is -1. So then the net work done must have been 0. Well, whew, that was, almost forgot to do that. Dot. Vector, vector, minus sign, not 1, not 1880, 0. Because friction is opposite the displacement. We pushed it that way, but friction was pushing us this way. So when we do the dot product, we got force times distance times the cosine of 180, which is a minus sign. And then when we add them, we get 0. This is great. This is perfect. In this situation, what is the net force on the box? 0. So by this thing that I just wrote, what should the net work be? 0. And we just proved, we just said it was. So our definition, apart from being a little bit arbitrary, is consistent with the larger whole. All the things that we would have to say, we are saying already. But there's one more thing I gotta tell you. Net force is MA. Right?
Yeah.
Now. Usually, almost always, if something is accelerated, at least in linear motion, we aren't talking about some kind of curve or like a circle or some sort of wacky shit like that. If we've got linear motion, X, Y, Z, acceleration and displacement are probably going to be in the same direction. We're speeding up or we're slowing down, but they're coaxial.
Wait, which one?
Acceleration and displacement.
Oh,
Basically, we're speeding up, we're going a direction. So yeah, that's all in the same direction, or possibly they're opposite.
like deceleration?
Yeah. But let's, for the sake of argument, let's say we're speeding up. If they're in the same direction, then we're asking for the cosine of not an angle, cosine of 0, which is just 1.
Is it 0 degrees?
Yeah, if acceleration and displacement are in the same direction, then there's no angle between them.
Oh.
All right. I gotta do a couple of kinematic things, kind of all in one step. Acceleration, we've got a kinematic formula for it. We had a relationship for squared velocities. Velocity squared is equal to velocity squared plus 2a delta, delta x or whatever. Since we're not talking about x or y, I'll use delta r stuff. So that's delta r, and we can cancel those. Division by 2, I'm gonna write it as multiplication by 1/2. Delta r is canceled. And we got m distributed through, and also the division by 2. Or multiplication by 1/2. Now, call me crazy. If this doesn't look like final something or other minus initial something or other, it looks like a delta. It looks like delta 1/2 times n times b squared. Evaluate this in the final state, subtract what we get when we evaluate in the initial state. This quantity, 1/2 mv squared, whatever it is, you don't have it if you aren't moving. If you are moving, the more your mass, the more of it you have. Or whatever your mass, the faster you're going, a lot more that you have,
Meaning work.
kind of. Meaning the effects of work. Think about pushing that box on the Oculus.
Oh,
After I'm done pushing it, that box is moving. Has some mass and some velocity. I did some work by pushing. What happened? It's moving now. This is the thing that you have when you're moving.
Acceleration.
Energy.
Blast.
What kind of, the thing about energy is it's really hard to define.
So we went from total work. Is it kinetic here?
Yes, it is. And I'm gonna bring everything full circle for just, we're gonna stop here, we'll pick this up later. In the pivot activity, y'all were just working on. When you graph distance versus speed, were your dots linear?
Fairly.
Not really. Did you get a better fit when you use like a quadratic?
Yeah.
Oh, yeah.
Let me say that again.
Yeah.
Did you get a better fit when you use quadratic? Speed squared
That made me think of
has something to do with the distance.
Are we
It
gonna
did-
get on quadratic formula?
What?
No, never mind. Are we gonna get on the quadratic formula?
I mean, we have one, I mean, it is quadratic, it's just easier to solve because it doesn't have, you know, the term.
Oh,
I'm saying the graph that you made linearized with square speed, and there's a good reason for that, because you measure the distance over which friction acts. Friction over a distance smells like work. Work is related to kinetic energy, which goes like squared. Why is the shape of your graph what it is? Or said another way, why is what we did sensible? Because the shape of your graph is what it is. So how can we just define stuff? Because it matches,
what happened?
is we have good agreement every time we observe something. We see a relationship like y'all observe doing the thing. Yep. Energy has a whole bunch of forms. I know.
Oh,
Energy is I can't tell you what energy is. I don't have a good answer. It has a whole bunch of flavors, and as far as we can tell, it's something that you cannot just make more of or fully eliminate.
Oh, yeah.
energy cannot be created.
Every situation we have ever looked at, the energy we have is the energy we have. It changes flavors, sure, but however much of it we have when we're done, different flavors, whatever. So what is energy? It's the thing that's sort of universally constant. How do I know I'm looking at energy if it did change? Add it all up, do I have as much as I started with? That's probably it. I don't have a good answer. It's gotta be joules. Joules. Because the units of work are equal to the units of energy. Gotta be joules. Super valuable. This thing, like jewels. Have an excellent long weekend, everybody.
Thank you.
Happy birthday. We see you.
Next week. 15.
Oh.
But at me on Discord as y'all are working tomorrow. And next week, if you're ready. Thank you. Thank you all for the extra like 10 minutes. That's pretty good. You do.
Oh, man.
Uh,
My house. What? No.
it's so sweet.